Okay, so for this talk, I'll be going over mainly two seemingly disjoint topics, but hopefully I'll connect them back together in the end. So this is just a little overview of what we're going to be doing today. Some reinforcement learning, quantum machine learning, and quantum RL, and the sort of future directions that hopefully you all can take this in. So first of all, I know you have covered some of the different genres, if you will, of machine learning, but it's important to distinguish reinforcement learning from previous paradigms of machine learning. So supervised learning is pretty standard in terms of what you think of when it comes to contemporary machine learning. You have some labeled training data or big data that you want to fit, and you learn some sort of function approximator for it. And so this might be learning to classify images or text, sentiment analysis, something like that. Unsupervised learning is based on pattern and feature analysis. So, for example, doing clustering or um, auto encoding, stuff like that, where you don't have any labels. You just look at the data and analyze it as is. And these are both pretty different from reinforcement learning, which is trying to learn how to maximize a numerical reward signal by interacting with an environment. And so this is a very different and arguably more challenging goal, not challenging as a research field, but challenging for an agent to do. Um, and so you often think of reinforcement learning within these environments in which the interaction has some impact on the environment. So you could frame reinforcement learning and learn to classify images with the reward being positive for getting it right, but that wouldn't really utilize what reinforcement learning is about because it's about this interaction. And so you might be asking, okay, but what really is RL? That's kind of a high level overview. And I really will just be sticking to the high level overviews. There are going to be some technical blurbs and equations and the like, but I won't go over them at all. They're just there for those of you more mathematically inclined. So we see in this picture that uh, the goal of reinforcement learning is to design an agent that interacts with an environment based off of seeing the state and the reward. And so you can see this sort of cyclic loop where it just gets state and reward, gives action, the environment updates. And this environment can be anything. It could be the real world, it could be robotic arms, it could be a video game where you take one step and you move to pong paddle up one. There's any number of things the environment could be, and that's part of what it makes reinforcement learning such an attractive field. And so how exactly do you do this problem? There's a lot of different techniques to do reinforcement learning. Two of the main sort of categories or types are model-based and model-free. And so that really, the main difference there is how it treats the environment it's interacting with. So model-based RL is either given the model, for example, in chess, you might be given the model and that you might know how the game works. Your agent might realize or know that if you move the pawn forward one, you're going to have some set of moves available after that because it knows how the game works, and so it can look ahead in the game. Or you could try to learn the model, and this is a particularly appealing field because in a lot of cases we don't always know all the complex dynamics of certain real world models, or programming all the physics and wind and all these interactions for some robot would be a real challenge. And so it can try to learn the mechanisms of the environment. However, another prominent field or domain is the model free algorithms. And these do not know anything and do not care anything about the environment. don't try to learn anything. You're not given anything. The environment is a black box that takes as input the actions and returns states and rewards. And that's it. That's the extent to which it knows and cares about the environment. And so, and to this end, there's a couple different ways you can do model-free RL. You can do value methods, such as Q-learning shown here, in which you try to estimate the value of taking each action in a given state and then simply pick the action with the highest value. Or you could also do policy methods where you directly update your decision-making process, or you can do actor-critic methods, which sort of combines the two, in which you have an actor that picks what decisions the agent makes, and a critic, which, such as some sort of value method, which informs the actor how good or bad the action was. And so, this is a lot of sort of there's a lot of new information, I know, and so it may just seem like a lot of math, a lot of technical mumbo jumbo, but what can it do? And so RL has certainly had a lot of well-publicized achievements in recent years. Here is a subsection of sort of one half, well, maybe more, but sort of one common area of application for reinforcement learning, and that is games. The other, which will be on the next slides, is robotics. And so here we can see, well, what can RL do? Well, it can get you a lot of cover papers is what it can do. Here we see a bunch of different prominent or well-publicized reinforcement learning achievements. Note that if you want to look at the citations, the PowerPoint is available, publicly shared, so you can check that out at the end. On the left, we see one of the papers that sort of started the whole deep RL boom, which is the Nature cover paper, Human Level Control with Deep Reinforcement Learning, which played the Atari games from Pixels. Only recently, however, that's what this second citation is, was Agent 57 announced, which actually achieves superhuman performance on all of the environments. Some of the 57 Atari games, the original Nature paper did not achieve superhuman performance at. Here we can see probably the most well-publicized event, which was AlphaGo, in which a computer beat the world's best Go player, Lee Sedol, at 4-1 in a well-publicized game of Go. Go may not be that popular over here in America, but in Asia, especially in Korea, it's of huge cultural significance. And for a long time, psychologists, cognitive scientists, researchers, and the like thought Go was too complex, couldn't be beat by an AI, because not only because there's just an insane number of actions every choice, there's hundreds of times more actions than chess, making it a massively more complex game to play than chess, but also because there's always been sort of a sense of beauty and a sort of creativity in the way a lot of the top players interact with the game. And so people thought that would be impossible to capture on a machine. But long story short, they were incorrect. And the next paper is a paper that beat AlphaGo 100-0. That may not seem that impressive. Obviously, we're always making improvements. However, it did this without human knowledge. AlphaGo was trained off of, it looked at a lot of pro players going through these huge databases, being like, okay, this is what the really good people do, and I'm going to learn from them. But this AlphaZero paper said, no, I don't need any human knowledge, starting from just the ground up, just the knowledge of how the game works and just taking random actions, I can achieve superhuman and super AI performance. And so that's a really significant area. An interesting area is the human independent gameplay. And then over here we see Grandmaster in all three races in StarCraft 2, which is a very different style of game, but an insanely complex one. You have to do hundreds of actions per minute and a huge environment space. Uh, Lots of complex long-term planning, literally 40 minutes games perhaps, which that might not seem long. Chess games go for hours and hours, but in terms of actions, if you're doing 100 actions per minute and it's 40 minutes long, then suddenly you have 40,000 actions and you have to plan that far ahead, which is extremely difficult. And so this is this sort of came not really out of nowhere, but StarCraft 2 has been a problem for a long time, and it sort of got, you know, I don't want to say solved because there's still a lot of work to do, but really well done recently. Um, and along the vein of StarCraft 2, there's also OpenAI 5, which beat, I think it was OG back-to-back TI champions in Dota 2, which is similar to StarCraft 2 in that it's visually complex, requires long-term planning, lots of actions. So it's a different style, MOBA versus RTS, but the complexity is similar. And so these are a lot of publicized, impressive achievements that RL has done, but sometimes people criticize them for not being rooted in real world problems enough. So that's sort of where the robotics aspects come in. And here we can see, I'll just play a little bit of this. OpenAI taught a robotic hand how to solve a Rubik's Cube. And so this requires, a lot of precision, a lot of dexterity. And so this robotic control is another area in which reinforcement learning is a very popular field. And here's also perhaps one of the most important aspects, and that is self-driving cars. We can see here a reinforcement learning algorithm that drives a car, and it's going very slow, obviously, but it's still pretty impressive and pretty culturally and socially significant. And so moving on, we have problems with RL. What can RL not do? And the answer to this question is probably a lot longer than the answer to the question, what can RL do? So I like this quote from a blog post by Alex Erpan. Whenever someone asks me if reinforcement learning can solve their problem, I tell them it can't. I think this is right at least 70% of the time. And this really gets to one point that I don't have up here, but it is important. Oftentimes, when you're considering reinforcement learning for a solution to a problem, there are much better methods than reinforcement learning. Supervised learning, like a lot of real world reinforcement learning problems can be reframed to supervised learning problems, or you can use different methods. For example, those of you who follow chess will know that Stockfish is the TCEC, or the chess computer champion of the world, I think the last 2 seasons now, against Leela Chess Zero, which is the AlphaZero inspired reinforcement learning agent. And so we can see that this, Stockfish is some sort of modified alpha beta pruning tree search, but we can see that this other methods work better. In a paper, I don't have it cited here, that came out a while ago, was showing that random search methods can often perform better than reinforcement learning. But into the problems now, we see one is that reinforcement learning is incredibly brittle, which hinders its applicability to real world situations. We see here on the right graph, looking at that yellow curve, we see this reward versus time graph. And we see that, okay, it's learning, that's a good thing. But if you look at the confidence interval, or the margin of error, perhaps, we can see even as it's learning and gets better, it extends almost to 0 for every single iteration. And so if we say, okay, this agent learns, but it could also at any given run just completely fail, just get 0 reward and abject failure, that's not good. That's not what we want in systems. And reinforcement learning is often insanely sensitive to hyperparameters, to environments to reward signals to all of these different things. A lot of papers have shown, for example, that I cited here, that the advantages, a lot of advantages gained by contemporary algorithms are non-existent, and that they're really a aspect of code level optimizations and little tricks that you're doing to improve it, either intentionally or unintentionally. And so, this is a huge problem for um, real world RL. And so, um, reinforcement learning is also really sample inefficient. It takes a huge amount of time to play Atari, which is a really simple game. It took millions and millions of dollars, days and days. AlphaStar literally trained for about, I think it was 48 days continuously on Google TPUs. And so this is insanely expensive and insanely inefficient, which is not something you want for the real world. You want TensorFlow Lite or these models that are easily deployed. And lastly, we have environmental impacts. This isn't really unique to reinforcement learning. It's just there because reinforcement learning is especially sample inefficient and therefore requires a lot of training and a lot of computational power. And we can see that a transformer with 213 million parameters, which is not a huge amount. I mean, it's large, but not insane. I think current language models like GPT-3 have something like 200 billion parameters. Takes, in order to train that, takes as much as 5 cars. And that doesn't even include deployment of this. Once it's trained, I don't have the citation for this, but a NVIDIA study estimated that 80% of the computational power is done through forward passes of using the networks. And so, there's a huge carbon footprint of machine learning that is kind of, hidden from all of us. We don't even consider it, and we might not even be aware of it. But it's something that should be concerning, considering the substantial impact. If we all just train transformers all day, that's a lot of energy. And so we have to shift into real world reinforcement learning. What can this, I mean, games are great, they're fun, they're excellent algorithmic testing grounds, but they're not as useful as a lot of what supervised learning has done. That's now part of Google search engines, Google Translate, images. All supervised learning is very much integrated into contemporary technological products, but not so much with reinforcement learning. There's almost no applications of reinforcement learning to the real world. There's a lot of challenges with this, as I've just presented, but it is a growing field. There's workshops and conferences, and there's a lot of social implications to what do we mean by real world reinforcement learning? Do we mean, okay, reinforcement learning that isn't brittle, or do we mean reinforcement learning that incorporates some sort of human centric paradigm? Do we mean, if we have a self driving car that always drives well, that's great. But if we have a self driving car that always drives well and doesn't have the same values that we do in terms of, presented with different actions, that's a important consideration and often gets dropped from real world RL discussions, which are usually just centered on how do we make RL stable and more sample efficient. So now I'm going to do a little jump, what seems like a jump at least, to something seemingly completely unrelated. And so we see, wow, straight to quantum computing. This is just a completely, seemingly tangential topic, but I'll merge them together later. So what is quantum computing? Once again, I'll give a high-level overview. There will be equations, but I won't discuss them. So basically, quantum computing is just computing using quantum bits, which exploit quantum mechanical properties. So we all know classical bits, either, we can conceive of it as a Turing machine or a von Neumann machine or however we want to think about them. But even it doesn't matter if you have this infinite tape Turing machine, it's always going to be a 0 or a 1, or I guess, you could have there's a lot of different varieties of Turing machines, but the bits are always 0s and 1s. And that's what they're limited to. You can flip between them, but you're going to have a 0 or a 1. Whereas quantum bits can represent both 0s and 1s simultaneously, and you can operate on these simultaneous states. However, it is notable that you cannot measure all of these states simultaneously, and you only get one value when you actually, analyze the quantum bit. So why do we Why quantum computing? Well, it allows for exploitation of two important quantum mechanical properties, superposition and entanglement. So superposition is basically what I just discussed. You can represent qubits as linear combinations, i.e., you could represent it as a linear combination of bit strings like 000, 001, 010, etc., etc. And so it can represent all of these simultaneously and operate on them. So this not only allows information representation to scale exponentially better than in classical computers, but it also allows operational efficiency to scale exponentially better because you can operate on all of these states simultaneously. An entanglement is when a state of quantum bits cannot be described, independently of the state of each other. And we see a EPR or Bell state at the bottom here. And so, I won't really talk much about entanglement other than saying it's important. And if you can understand it, you're smarter than Albert Einstein. No, I'm just kidding on that last point. But the EPR state is named after Einstein and two other physicists who famously doubted quantum mechanics. And turns out the EPR state can exist, even though they were skeptical of it. So, how do you do quantum computing? Well, you can either do it with a lot of money and a lot of ice. You have to freeze these quantum chips down insanely cold to allow these quantum mechanical properties to be exploited, or you can do it on a classical simulator, which is what most researchers do, myself included. So, quantum computing is sort of a different uh, programmatic approach to computing than we're used to. Normally you just open up your favorite language, C++, Python, whatever it might be. You get typing in that language, you can implement any algorithm you want. However, underneath all of that are real classical bits abstracted away under many, many layers of abstraction, from classical to bit strings to the assembly language, x86 or MIPS or whatever, to C, to Python. All of it is very much hidden. That is not the case in quantum bits because you almost always directly work with the bits and the quantum gates. And the reason for this is simply because of the power of the quantum bits. If you have to do everything with classical bits on a classical computer, you'd probably go insane. Having to write and complicated programs from bits would be insane. But if you consider, just 64 qubits, that's not too complex to work with, can represent 2 to the 64 states. That's insane. That's an insane, a huge amount of information that you're working with. And so because of their power, you can work directly with them. And so what can we do with all of these fancy techniques? Well, we can do a lot of techniques, or a lot of improvements. We can get super polynomial or very, very big speed ups for a number of problems. I've bolded a couple. Importantly, factoring and discrete log, and we can get polynomial speedups for searching and machine learning. And I've bolded, there's other ones you can see up there, but I've bolded the important ones. So why is factoring and discrete log important? That's sort of what actually catalyzed the entire field of quantum computing for the most part, or at least generated a lot of interest in it, because this is what is known as Shor's algorithm. And you might think, factoring, who cares about all this? Great, we can do these fancy math functions faster. Why does that matter? Well, factoring and discrete log are the basis of many public key cryptography systems. RSA is basically just built upon the inability of other people to factor giant prime numbers, and so, or relatively prime numbers. And so it's important to realize that super polynomial speedups and factoring breaks down a significant portion of contemporary cryptographic protocols. And that's why people are like, hey, wait a minute, this quantum computing thing isn't just for the physics nerds like Feynman who sort of inspired it. It has real and important significance, and everyone, the first person to get Shor's algorithm on a real quantum computer is a very powerful person. And polynomial speedups are for searching. This is Grover's algorithm and machine learning, and this is what I'm going to be talking about now. So what is quantum machine learning? It's a very, catchy or jargon-laden term, but really what it is just combining quantum computing and machine learning techniques. So you can use some sort of parametrized quantum computer to learn a function approximator. And so you can uh, do a lot of things with this, but it's important to have a method or a way to do this. And usually this is done via simulators. Here you can see a couple examples. You might not notice this, it's a little before our time, but two prominent simulators are named after Beatles songs, which I have put the associated lyrics to surrounding them. And then, so there's a bunch of different simulators that you can use for different tasks, quantum machine learning, general quantum computation, photonic techniques. There's a lot of different things. And so that's pretty much how a lot of research is done, because you can simulate noise, you can do a lot of things on simulators. And so what can you do with these techniques? Well, there's a lot of different algorithms, a lot of different quantum versions of classical algorithms like hot field neural networks, support vector machines, perceptrons. And specifically what I want to talk about are quantum neural networks or quantum variational circuits. Neural networks, that's sort of a vague almost term in the quantum world, because unlike with classical neural networks where you just have the input of one node just go to all the other nodes of the next densely connected layer, you can't do that quantumly, because the no cloning theorem states that you can't clone any quantum state, so you can't just pass it around like that. But there is some sort of similar ideas between quantum variational circuits and classical neural networks. And so a quantum variational circuit is a similar paradigm to deep learning, but with mathematical differences. You have three important parts to a quantum variational circuit: an encoder, a parametrized circuit, and a readout operator. So basically you encode classical or quantum data into appropriate quantum states. You evaluate your parameters that you have, then you extract information from the quantum circuit, and then you calculate a loss function, and you can optimize them in any number of ways, including gradient descent, because the quantum variational circuits are differentiable, which enables hybrid models. And so what can you do with all of this? Well, there's sort of four different fields related to this, but specifically looking at quantum algorithms, you can work with classical data or quantum data. A lot of people think that quantum data may be the area with the greatest potential speed up, because you don't have to worry as much about converting data if you just have naturally quantum data. That's not to say that there isn't potential speed up in classical data, it's just quantum data seems more easily applicable. Classical data requires you to convert into quantum data, and a lot of approaches for optimal or amplitude encoding require exponential number of gates, which sort of negates any sort of exponential advantage you would get from the state representation. So there's a lot of challenges with encoding. That's very much an active area of research. And so there's a lot of different cool applications of quantum machine learning, eigensolvers, a lot of quantum chemistry stuff, quantum GANs. You can do all sorts of stuff with it. But there's still a lot of problems. The barren plateaus problem, or vanishing gradients, exists in quantum and parametrized quantum circuits. It's hard to convert classical data, and hardware is very much a challenge, or so I'm told. I don't really do anything with hardware, but those people always say it's very hard. A lot of noise and not a lot of qubits. We're stuck with in the tens usually of qubits, and in order to prevent sort of any interference or decoherence of states, it's hard to make the hardware to do that, and there's a ton of noise, and so there's a lot of challenges in the hardware for now. They always say quantum computing is 10 years away, every 10 years, and yet it's not here yet, so we'll see what happens. So now I'm going to sort of bring it back together. Quantum reinforcement learning. So we know reinforcement learning is sample inefficient and there's a lot of problems. And we know QML has a lot of power, representational power, and few parameters. And so we can see, hey, wait a minute, is this a match made in heaven? There's a lot of different techniques. I'm not the first guy to think of this. And so it seems there's a lot of promising work. And so here we get to our work in which we show that using a quantum variational circuit for function approximation in existing reinforcement learning algorithms can work very well for reinforcement learning tasks. Here we see a comparison with a neural network with thousands of parameters when the quantum variational circuit only has about 50. And so there's a lot of power there with a lot less effort, you might say. And this is a continuation of the work. You're welcome to check it out if you're coming to the Neural Information Processing Systems Conference 2020, the end of December. So what can you do? There's a lot of opportunities. You can take classes, you can get involved with research. You're welcome to contact me. So yeah, there's a lot of potential research options that you can get involved with. And I encourage you to, be active, explore, create, and get involved. So yeah, that's pretty much all I have for my talk. That's pretty much, I was going to go for 30 minutes and I'm right at 30 minutes. So if we have questions, that's good. If not, that's fine. Here, I'm just going to skim through the citations real quick just to make sure I do, in fact, get all of them. You can see I have all of them. And so, yeah, I'm going to call it here. Thank you for having me, and I hope you all enjoyed the talk.